Hello, today we continue solving a problem using the gas laws. In this case, the two problems we are going to solve are united by one formula, one equation. This is the equation of state of an ideal gas. Let me remind you that the formula of this law, this equation, is P times V. N is the mole number, the gas constant, and the temperature. So both problems will be solved using this equation. Now let's see what it tells us in the first problem. The mass of hydrogen taken as 2 kilograms is known. The temperature at which this mass is measured is 25 degrees Celsius. That is room temperature. The pressure exerted by this gas is 1 atmosphere. And we are asked what volume this gas, hydrogen, will occupy under these conditions. So we have to use this formula. Pay attention to the fact that we're given the temperature in Celsius. You have to remember to do this because you can't substitute the temperature in Celsius into this formula. We explained in one of the lessons why the gas laws work with temperature expressed exactly in Kelvin, so let's do the translation. The temperature will be 25 plus 273, and it will equal 298 in Kelvin. Now let's convert our formula to find the volume. To find the volume, we need the number of moles multiplied by the gas constant, by the temperature, and divided by the pressure. Now let's see. Do we know the number of moles in this case? No, we don't, because the mass of our hydrogen gas is given. Then let's convert this formula so that we can use it. For this number of moles to find, we divide the mass by the molar mass, and we have our known parameters. The universal gas constant, temperature, and therefore pressure. Let's make a substitution, but let's not forget that we have the mass of hydrogen in kilograms, and we work with molar mass. Let's not forget, there the calculation is in grams per mole. Then we will convert the mass into grams. It is 2,000 grams. Now let's make a numerical substitution for the calculation. So the mass of hydrogen is 2,000 grams. Multiplied by the gas constant. But note, we've got the pressure in the atmosphere, so we've got the universal gas constant. So that's 8,205, 74, times 10 minus 2. And it's all in units of liters, atmosphere. Respectively, Kelvin, minus 1, and mole, in minus 1. And then we've got temperature on top of that, which we've converted to Kelvin, multiplied by 298 Kelvin. And then we've got the molar mass at the bottom, which is 2 grams per mole, and multiplied by the pressure. And the pressure is 1 atmosphere. So let's check if we have the reduction going through correctly. We have grams reduced, we have atmospheres reduced, we have kelvins reduced, we have moles reduced, and so the answer is 1 in liters. But when we do the calculation, we get in liters. 2,004,4553. 1 in liters, but let's write down more conveniently so that it's a number more compact. 2 whole 44531 times 10 onto the 4th power, and that's in liters. That's it. We've got our answer. Let's move on to the second problem. We know that we have taken the volume of carbon dioxide. The temperature of this process is also given to us, and the pressure is given in kilopascals. We need to find the mass for CO2. We work with the same equation. But in order for us to cope, we need to work out what the mole number is. its mass divided by molar multiplied by the gas constant and by temperature. So in this case, we need to find the mass. But don't forget that we are working through the temperature, and the temperature must necessarily be in kelvins for this 22 at 273. And we get that this value will be equal to 295 in kelvins. All now from here we derive our mass. To find the mass for CO2, we need P times B times the molar mass and divide by the gas constant and by the temperature. So we all do numerical substitution in this case. So the pressure of the problem is 500 kilopascals. Then multiplied by the volume, and we have a volume of 200 liters. The molar mass for CO2 is carbon 12, oxygen 16 times 2, 44, and that would be in grams. In terms of moles, so divide that by the gas constant. Note it has to be in terms of kilopascals, and that's 8. 31447 in liters, and then kilopascal. Multiply by Kelvin minus 1, and a mole in minus 1, and then multiplied by the temperature, and we've thoughtfully converted the temperature to kelvins. 295 kelvins. All do the check, and so we reduce kilopascal, kilopascal reduces, kilopascal reduces, mole reduces, mole reduces, liter. So, and the answer we will be respectively in grams, because in addition, kelvins, everything remains to calculate mathematically. It will be 1793.89 in grams, or if we translate, for example, into kilograms, it will be 1 whole 799389, but that would be 1 kilogram. In any case, the answer is found, and in this case, we use the equation of state of an ideal gas as a solution to the problem. I hope you understand. Goodbye.